The atoms in molecules and lattices are combined in a fixed ratio. The example we had was the example of water. In water, we have one oxygen atom, which is here, the one in red, which combines with two hydrogen atoms. You'll see that. So all water molecules consist of one atom of oxygen and two atoms of hydrogen. This combination is what gives water its specific properties. Notice that if these atoms of hydrogen and oxygen are combined in a different way, in a different ratio, then the result will not exactly have the same properties as when they are combined, when they are found in water molecules. Although the elements, the atoms must be of the same elements, hydrogen and oxygen, the combination, the way, the manner in which they are combined matters a lot, and it determines the specific properties that this resulting molecule or the bigger picture, the compound, would actually have. We'll see here, for example, we'll still see hydrogen atom, two of them, but this time instead of one oxygen atom, we have two oxygen atoms. This is typical, this is the formula, the molecule of hydrogen peroxide. So hydrogen peroxide, although it has hydrogen and oxygen, just like water, but because of the different way of combining and the different ratios, remember with water, with water it was two atoms of hydrogen with one atom of oxygen, 2:1. In hydrogen peroxide, it's two atoms of hydrogen with two atoms of oxygen. Here is 2:2. So the properties, the chemical properties, will be very different from that of water. Similarly, we would have, if the atoms are coming from different elements in a crystal lattice, then the molecule would also be different, then the compound would also be different. In this case here, contrarily with what we had earlier with sodium chloride, 1:1, this time those were atoms coming from sodium and chlorine respectively. This time our crystal lattice is formed from atoms coming from iron and oxygen to form iron oxide. Hence, the chemical properties will be different, just like when we compared water and hydrogen peroxide earlier. Now, when compounds are formed, we don't just leave them like that. We also try to give them a unique name and formula, because elements had a name and a formula. When elements recombine to form compounds, then we are also supposed to give these compounds or these new entities a name. Hence, for example, water is represented by the formula H2O. Okay, very famous formula. It's presented by the formula H2O. That's water. When we look at the formula, we see some figures. We see here in subscript 2, and here on O there seems to be nothing. That's just taken by conventionally. O there should, where there's nothing, there should be 1 there. That's by convention. Conventionally, we don't put 1 there. It's just like when you're looking at X and comparing X and 2X. In front of X, you have, when it's 2X, in front of that 2X, you have a constant which is 2. It's represented. But when you look at X, we assume conventionally that there is a 1, an invisible 1 in front of that X. The same thing is happening here. We have H2O in subscript, we have 2 because it means that 2 atoms of hydrogen. Then we have nothing here. Imaginarily, we have 1 there because there's 1 atom of oxygen. Okay, so from this point, with what we've seen earlier, can you, for example, give the formula of hydrogen peroxide from the previous example on molecule of hydrogen peroxide? Remember, we had 2 hydrogen, 2 oxygen. So similarly, we had for water 2 hydrogen, 1 oxygen, you then should be able to give us the formula for hydrogen peroxide. The same way, you should be able to give the formula units of the type of iron oxide that is formed in that previous lattice where we had 1 iron and 1 oxygen combining specifically in that ratio to form iron oxide. Okay, we have been saying that when compounds are formed, the elements somehow react and the atoms recombine to form these compounds. But then these atoms are held together to form molecules. The question is, what holds these atoms together? When atoms combine to form molecules or to later on form compounds, they do so because they experience an attractive force between them. It means one atom comes from this side, another atom comes from another element. They get attracted together to form a bond that we call a chemical bond, which is created as a result of the forces that hold these atoms together when they are about to form a molecule. So chemical bonds exist between atoms that form a molecule. Now, during chemical reactions, compounds form. But remember, in this case here, this is a compound that has formed. Otherwise, I'm picking up here a molecule of water, okay, which is the smallest portion of a compound. Now, let me just generalize that this is my compound here. During a chemical reaction, these compounds don't just form from space. No, I must have something that is existing added to another something that is existing. Then I can form an existent entity that I'll call a compound. Okay. Now, for these two to combine to form my compound, there must be a form of chemical reaction. Okay. And in that chemical reaction, the atoms, I have atoms here, the atoms that are found in the molecules, I have a molecule here, rearrange themselves. Because at the end of the day, I want to have a specific pattern, a specific ratio here in the compound level. For me to achieve this, there must be some sort of rearrangement of atoms, of individual molecules, of individual elements, such that I can then get the compound. So these atoms rearrange themselves in a specific way so that I can then have a compound being formed. Okay. For this rearrangement to take place, nonetheless, bonds must break. The bonds that were joining these atoms to form this molecule here, for example, must break. And the bonds that were also joining these atoms in these molecules must also break, such that each atom is now free. They must find themselves at an intermediate state. I'm saying intermediate because they are now halfway between what they used to be in the molecular form and halfway between what they will be in the compound form, in the molecular form of the element and in the compound form of the element. There will be an intermediate form where we have free atoms seeking each other, trying to rearrange themselves. And the arrangement they finally come up with will then determine the specific property of that compound. If they then rearrange themselves, I'm here having hydrogen, oxygen. If the rearrangement makes them behave such that they want one atom of oxygen to combine with 2 atoms of hydrogen, then my result will be water, and water has its own specific property. if at sorry, if at that intermediate state they decide that the rearrangement should be rather 2 atoms of hydrogen should bond with 2 atoms of oxygen, then my resultant here, according to the example we had earlier, would be, I'm sure you've seen it already, hydrogen peroxide, which will behave differently from water because it has its own specific property different from water. Okay, now when we look at this example here, we have 2 sides. We are having here an equation. We have the left side, because we're working from the equal sign that we have here, working from this equal sign, so that we have 2 sides. We have the left side and the right side of the equal sign. On the left side, we are looking at 2 molecules here, 1 and 2. These are called the reactants because they are the ones who are going to go into a chemical reaction. They are on the left side. What we form here now, on the right side, the compound that we are going to form will be what we'll call the product, because it is what is achieved at the end of the reaction between the reactants. So we have in this system, we have in this whole in this whole system, we have 2 aspects. We have reactants and products. Bonds in the reactants are broken and rearranged in the intermediate state to form new bonds in the product, otherwise the compound. Okay. A compound hence gets to have or gets a chemical formula. And notice, like I said earlier, when we're looking at a compound is made up of molecules. And a molecule of a compound is a representative of the whole compound itself. Hence, if we isolate a molecule, the chemical formula of that compound should be the same for any molecule of that compound. Okay, for example, H2O is a molecule of water, is the formula for that molecule of water, but that formula is the same formula for the compound called water. Okay, so like I explained earlier, we can read the formula of such a compound or a molecule and consider the subscripts, which will tell us how many atoms will be present in a particular element found in that molecule of that compound. So, like we did with water, for example, with water here, we have 2 elements. Notice, we have hydrogen and we have oxygen. Okay, 2 hydrogen atoms, 1 oxygen atom. The subscript here, 2. The subscript tells us that there are 2 hydrogen atoms in 1 molecule of water. Okay, 2 hydrogen atoms in 1 molecule of water. Again, similarly, it also tells us when we're looking at oxygen, there is nothing here. It's supposed to be 1, but conventionally, we want to say that there is a 1 there. So this tells us that for each molecule of water, we get 1 oxygen atom. Just 1 oxygen atom in each molecule of water. So when we write H2O, we mean H2NO1. Okay, according to convention, that's what we'll have, H2 and O1, but the 1 is kind of silent or imaginary, so we don't include it there. Okay, so that's it. The ratio will be, at the end of the day, 2 atoms of hydrogen, 1 atom of oxygen. Our ratio will be 2:1. So then those will be your activities. You will refer to your textbook, the one you have on ITS. You'll go to the one platinum. You go through pages 262 to 264. You'll have activities based on what we have covered so far. Thank you very much for attending. Have a nice day.